In this video, we're going to derive some identities, or in other words, prove why the identities we learned about yesterday are true. So we're going to start this video with the difference identity for cosine. If you recall, that's the one that looks like this. Cosine of the difference between two angles is equal to cosine of the first angle, cosine alpha in this case, times cosine beta, plus sine alpha times sine beta. I ran out of room here because I forgot. I put a couple links to other videos, other mathematicians on YouTube that have shared their thoughts on the proof of these identities. So if you'd like to type these URLs into your web browser, you can go to other videos and see how they've done their proofs. If you do choose to go to each of these videos, though, please remember that each of these letters is case sensitive. So this is a capital O, not a lowercase o, not the number 0, but capital O, lowercase b, lowercase a, capital A, and so on. These web addresses are case sensitive. But back to my example, we're going to start with this identity. I find that starting with the difference identity for cosine makes the following arguments a little bit easier. So before we actually do any math here, let's just talk a little bit about what's happening with these two separate angles. On this unit circle on the left-hand side, I'm just going to draw the location of a particular angle, and I'm going to call this angle alpha. So this line here represents angle alpha, and this line, let's say here, this one's going to represent angle beta. And I've just changed the colors to make these angles stand out a little bit more. So this green angle here, this is alpha, and then the blue angle is beta. We always measure from the positive x-axis here, and that's where alpha and beta come from. To make this proof more effective, rather than focusing on the angles themselves, I'm going to focus on the coordinates that come from each of those angles. Now, since this identity works for any angle on the unit circle, it doesn't have to be one that we've memorized. What I want you to remember is that the x value of any angle would be cosine evaluated at that angle, and the y value of this data point would be equal to sine evaluated at that angle. So I've got cosine of alpha and sine of alpha. Similarly, this point here would be cosine of beta and sine of beta. And to help illustrate my point, again, we're not going to be focusing on the angles as much as we are focusing on the two data points. What I would like to do is find the distance between these two data points. And if you remember way back to algebra, we have a calculation that allows us to calculate the distance between 2 points. The distance between 2 points is the square root of the difference of our two x values, so x1 minus x2 squared plus y1 minus y2 squared. Now we're going to get two y values. They come from the sine calculations. And we're going to get two x values. Those come from the cosine calculations. So even though this is an algebra formula, we'll be able to use it in the context of trigonometry here shortly. So the last thing that I'd like to do as far as setup goes before I begin the proof, or before I begin this derivation of the identity, is I'd like to rotate this gray angle that's formed. This gray angle in between alpha and in between beta, this is really alpha minus beta, right? This is the angle alpha minus beta. And I have a problem with this because it's just kind of floating out here in space. It's not anchored anywhere. And if I could rotate this to any position on the unit circle. But here's what I'd like for you to focus on. I would like for you to imagine that this angle has been rotated so that this leg, this right-hand leg of the problem, where beta is, I want that to be anchored on the x-axis. And when I swing that leg down to be anchored on the x-axis, then this left-hand leg of the angle also comes with it. And if I were to rotate it around, it might end up here. So again, this leg here has been rotated down to this position, and this leg here has been rotated up to this position. And what we've done with this, what I've hoped to preserve, was the distance between this data point and this data point. If I measure the distance along this dotted line, it will be exactly the same as the distance between this this green point and this blue point. So this distance through here is what we're going to continue to focus on. This distance should be the same as this distance. That's going to make our argument a lot more valid. As it turns out, for our notation here, because we've just rotated this, because we've just moved this alpha minus beta, again, in gray we had alpha minus beta, but we also have in red now alpha minus beta. The x value of this particular data point is cosine of alpha minus beta, and the y value is now sine of alpha minus beta. And I think you're starting to see why I chose to set the equation up this way, because this is what's going to help us establish the difference identity for cosine. We're going to get, we're going to do some math here and get this cosine of alpha minus beta that we're looking for. Now, typically when we establish identities, we don't work on both the left and the right hand side of the equation. But for this one, we're going to have to, because what I'm going to do is I'm going to focus on this gray angle that was drawn and this red angle that was drawn simultaneously. I think from a geometric point of view, it makes sense that these two angles are the same, so we're going to mirror that argument using our algebra simultaneously for both angles as well. So what I would like to do is start with the distance formula that calculates the distance between our green and blue points. And then I'm going to use the distance formula for this solid black line that I drew in as well. So I'm going to pause the video and fill this in. I would encourage you to pause the video and copy this next line as you can, so as you have time to do so. Okay, so here's the first line. On the left side of my equal sign, I've used this distance formula as a template, and I've subtracted x1 minus x2. So x1 coming from this cosine, x2 coming from this cosine. And I've squared that result, and I added to it y1 minus y2. And again, the y values for the left-hand side of our equal sign come from sine of alpha and sine of beta. On the right side of the equation, I have cosine of alpha minus beta. That's my x1 value for this data point. And I also have the number 1, because the other x value was equal to 1. We fixed that data point here at the beginning of the unit circle. So I've got x1 and x2 in this case. And similarly, the y value comes from sine of alpha minus beta, and the other y value comes from the original starting point of our unit circle located at 1, 0. So the y value was 0. All right, from here, it becomes an algebra problem. What I'd like to do is simplify and rewrite both the left and the right-hand side of the equation. And we're going to do so until we end up with this identity, until we get an expression that looks like this identity that we started using yesterday. All right, so here we go. What I notice is that I have a square root on both sides of the equation, and what I'd like to do is eliminate the square roots wherever possible. That'll allow me to work with the values that are underneath the radical signs. And we can do that very easily as long as we square both sides of the equation. So squaring both sides of the equation eliminates that radical symbol. We can do that because the operation that we've chosen to do is applied to both sides. I'm going to pause the video and fill in the next line now. Okay, that's done. Now for the next line, I'm going to expand each of these binomials. As you recall, when I have a binomial squared, that means to multiply the binomial times itself. So I'm going to write in the next line each of these binomials expanded. Now this is going to take up some more space, so I'm going to zoom out on my page here. Let's make sure that you have enough room to work side to side in this next step. I'm going to pause the video and fill in the next line. Okay, so that line's done. You'll notice that everywhere that there was a binomial squared, I just wrote that out as that binomial times itself. With the exception of the last binomial in this problem, sine of alpha minus beta minus 0. Well, that's just the same as sine of alpha minus beta. So when that's squared, I get to write it this way, sine squared of alpha minus beta. And if you see this line and think you'd like to FOIL these groups together, I think that's actually a very good next step. So that's what we're going to do. We're going to FOIL each of these pairs of binomials. I'll pause the video and complete that step. You should pause the video as well and try this on your own too. Okay, so a lot of foiling going on there. And this expression is starting to get awfully wide on the page here. It's taking up a lot of space horizontally here. But good news is that I think we've made this problem as complicated as it needs to be. From here, it's going to get a lot more simple. Hopefully what you're starting to recognize is that we're getting pockets of these cosine squareds and sine squareds, and maybe you're starting to think that we get to use one of our existing Pythagorean identities. And if you're thinking about that, then you're absolutely correct. So what I'd like to do is I'd like to grab this cosine squared and this sine squared, and I'm going to put them together at the beginning of this next line. So I'm going to write cosine squared of alpha plus sine squared of alpha. I'm going to put that at the beginning of the line. And you probably have a good idea as to why I'm going to do that here. Similarly, I want to grab this cosine squared of beta and this sine squared of beta, and I'd like to put them together as well in this next line. So I have now cosine squared of beta plus sine squared of beta. And again, you probably recognize why I'm doing this. I'm going to take advantage of the Pythagorean identity. So in essence, I've used this piece, and I've used this piece, and this, and this. I've used those four pieces from this line, and I've just rearranged them into a different order. I still have left over this minus 2 cosine alpha cosine beta, and I also, see, I just used that piece, so I also have this one here, minus 2 sine alpha sine beta. So that's the left side of the equation just rearranged and cleaned up a little bit. The right side of the equation behaves very similarly. So I'm going to cross that one out since I've cleaned up the whole left-hand side. Now this cosine squared and this sine squared are going to be grouped together. So cosine squared of alpha minus beta plus sine squared of alpha minus beta. Those two are going to be grouped together here. So now I've rewritten that and I've used those terms. That means I have left over this minus 2 cosine of alpha minus beta plus 1. All right, so now the real math magic happens. The reason why I grouped these numbers as they are is we know from our Pythagorean identity that these groups in parentheses are literally just equal to the number 1. Cosine squared of one angle plus sine squared of the same angle, according to our Pythagorean identity, will always equal 1. So this one and this one add together to make the number 2. And we have left over just this minus 2 cosine alpha cosine beta minus 2 sine alpha times sine beta. So that significantly cleans up the left side of the equation. And on the right side, we've got something similar still. we've got this group of the equation that's equal to the number 1, combined with this number 1 that's left over here on the right side. We also have the number 2 minus 2 cosine of alpha minus beta. Try writing that again. Alpha minus beta. At this point, I hope you start to recognize that there is a GCF for each of the terms on the left and the right-hand side of the equation. That's the number 2. So I'm just going to make this stand out real clearly here. If I factor out that GCF of 2, I'm left with 1 minus cosine alpha cosine beta minus sine alpha minus, sine alpha times sine beta. Close that parentheses, and that's equal to the number 2 times 1 minus cosine of alpha minus beta. So to clean things up, I can now divide both sides of the equation by 2, and as long as I apply that to both sides of the equation, then it's a legal algebra move. In doing so, that gets the GCF of 2 out of the way. And we're now left with 1 minus cosine alpha times cosine beta minus sine alpha times sine of beta. And that's equal to 1 minus cosine of alpha minus beta. Let's see here. Let's subtract 1 from both sides of the equation. That'll get the 1 over here to cancel, and that'll get this 1 over here to cancel as well. So we're now left with negative cosine alpha times cosine beta minus sine alpha times sine beta, and that's equal to negative cosine of alpha minus beta. Oh boy, we're almost there. Now, what I don't like about this expression here is that I've got negative signs all over the place. So what I'd like to do is add cosine of alpha minus beta to move that to the left side of the equation. I'm adding that to both the left and the right-hand side. And then I'm going to add this group to both sides of the equation and this group to both sides of the equation, effectively just moving these items across from the equal sign. And what that leaves us with is a positive cosine of alpha minus beta is equal to a positive cosine of alpha times cosine of beta plus sine of alpha times sine of beta. And wouldn't you know it, this is our identity. What we were able to prove in all of these steps is that the difference of two angles inside of a cosine function is equal to cosine evaluated at each of those angles multiplied together plus sine evaluated at each of those angles multiplied together. And we were able to prove that in about half of a sheet of paper. Not too bad.